Okay, so good afternoon again. We will continue our class on chapter 3. So last week we have learned multiplexers, decoder and encoder, adder, done, subtractor and sign number. So how we subtract the number and add the number in digital hardware, and the reason why we use adder in subtraction operation, right? And today we will continue from here, starting from comparator, multiplier, and ALU. Last week we have learned here, and also the adder subtractor unit. All right, so this circuit can be used to add and sub numbers in digital hardware, and this is the circuit that is used in the computer in the ALU. So this circuit is very important to perform arithmetic operation. And last week also I have asked you to go to view my video on YouTube regarding this one, how you write the code, how you design this using quarters prime, and how to simulate the circuit, right? So you can get the tutorial from there, and also the explanation. Today we will look at this arithmetic overflow. What is arithmetic overflow and why it is important? Uh, so the result of addition or subtraction is supposed to fit within the significant bit used to represent numbers. So when we design the digital hardware, so because this is hardware, it is limited, not like our brain that we can have any number and we can calculate any number. But for digital hardware, there are limitations in terms of the size of the processing unit. Right? For example, the adder, if our adder is 4-bit, so the number that we can use to add is 4-bit, and of course the result is 4-bit. If the hardware is 8-bit, so the number will be 8-bit and the result will be 8-bit. But how if we want to use or to perform the add and sub operation on uh, uh, a bigger number, or how if, for example, when we add, the result is more than the size, the space for the result that we have. For example, for 4-bit, right? So if we have two numbers, and in sign number operation, 4-bit, the maximum number for positive value is positive 7, and minimum number for the negative is minus or negative 8. So for example, if we add two number, right, 6 plus 2, the result should be 8, but 8 is not fit in uh, in the result storage or for the result. So that is the problem with digital hardware. So we need to know whether the result from mathematical operation, arithmetic operation, is fit in the for the uh, result or not. Yeah? The result is fit for the system that we have or not. For example, if our system is 4-bit, so the result should be 4-bit. But what if the result is more than 4-bit? For example, 6 plus 2, we have 8. So in order to do that, we need to have more spaces, right? So normally, later on in chapter 4, the result of any operation will be saved in the what we call a register. The register is the storage circuit. Yeah. So normally, if the output is not fit in one 4-bit storage, so we need more storage. So we need to use 2 register, for example, right? But we need to know, whether the operation that we perform is will produce the what we call overflow or not. Overflow means that the result is not fit in the for the not fit for the system. All right. Uh, so if the result does not fit in the range, so this is the range, the formula for the range, minus 2 power of n minus 1, and this is the minimum, and this is the maximum, 2 power of n minus 1 minus 1. So if our system is 4-bit, so 2 power of 3 here is minus 8, minus 2 power of 3. So minimum is minus 8, and the maximum is 8 minus 1, which is 7. If our system is 8-bit, so this 2 power of 7 to 1 to 8, all right, and this one 2 power of 7 minus 1, positive 1 to 7. If 16-bit, yeah, n is 16, and so on. So if the result is not fit, we call, or we can say that arithmetic overflow has occurred. Means that we have what we call the arithmetic overflow. So now we want to design a circuit that can detect this, that can know that this arithmetic overflow has occurred, right? So how to do that? Before we can do that, we need to understand what is arithmetic overflow and how is it generated, right? So we need to look at this example. So for example, our system is 4-bit, and let's look at this example where both number are positive, plus 7 plus positive 2, and the result in decimal it should be 9. So we human to do this calculation is easy, but in hardware there is not that easy. First, the hardware need to do in binary. Okay, so why we use binary in hardware? Why we not use decimal in hardware? Because decimal cannot be represented by the hardware, but binary we can represent in hardware, because in binary we have only 2 numbers, 0 and 1. All right, and to represent number 0 and 1 is easy. We can use a switch. All right, switch open means logic 0, or switch off, logic 0. Switch on or switch close is logic 1, right? And the switch is easily can be implemented using transistor. All right, that's why in digital electronic, we say that we have the transistor, or we implement the logic in using the transistor. So when you're talking about the latest microprocessor technology, for example, right? So people are talking about the number of transistor in your microprocessor chip. Right? So that microprocessor, that transistor is actually used to represent this binary value. Okay. So in digital hardware, every operation need to be performed in binary, and also we need to check whether the result is fit or not with the system. If our system is 4-bit, we need to make sure that the result is 4-bit. If more than that, we need to have, or we need to do something to process uh, or to solve that problem. All right, maybe we use more space in order to save the result. So in this case, 7 in binary is this, and 2 in binary is of course 0, 0, 1, 0. And when we add bit by bit, we have this 1, 0, 0, 1. If this number is unsigned, then should be no problem. All right, 7 plus 2, we get 9. But the number in digital hardware is a signed number, right? And we represent the negative number with the 2's complement representation. We have learned this last week. So let's see this. 7 plus 2, we have 9. And we know already from here that if our system is 4-bit system, the range for the result must be in between -8 to +7. And 9 is more than +7. And this means overflow occur, right? This is overflow. This is not fit in 4-bit system. And when we look at the result at the number here, this is +7. Why +7? When we look at the sign bit here, this is positive, 0. This is sign bit, so this is +7. This is +2. All right, +7 plus +2, the result must be positive. Positive plus positive number, the result must be positive, right? But you look at the result, the sign is negative, means that this one is something wrong already. So fast check, you can fast check actually when you do addition or subtraction in digital. All right, so if positive plus positive, you have result negative, means that something wrong, and that something wrong is actually overflow. Or negative minus negative, right? Negative number minus negative number, you should have negative result, right? But if you get positive result, means that something is wrong with your result, and that is because of overflow, right? And if we observe these two signal, right, C3 and C4, where is C3? If I can write here, we have positive 7 and positive 2. We add 1, 0, 1. This is again 1. C, this we call C0, and C0 in this case is equal to 0, right? This one at this one, we have S equal to 1, but C carry equal to 0 in this case, and we call it C0 here. 1 plus 1 is 0, 1. Sorry, this is not C0. This is C1. C0 is before. This is C1 equal to 0. 1 plus 1 here, we have S equal to 0 and C2 equal to 1. So this is C2 equal to 1. And 1 plus 0 plus C, because C2 equal to 1. So we need to plus. So we have 0 and we have 1s here. So this is C3, and we have 1 here. S equal to 1, and of course we have C4 which is equal to 0. Yeah, C4 is the carry from this operation. This at this we have C4. So in this case, we observe these two signals, C4 equal to 0, C3 equal to 1. Right? So we have C4 equal to 0 and C3 equal to 1 in first case. And look at the second case where here is minus 7 and this is positive 2 plus, and the result should be minus 5. Right? So minus 5 is actually within the range, right? Remember, the range is minus 8 to positive 7. So minus 5 is within the range. So the result should be no issue, no problem with the result. And when we add also, yeah, this 1 plus 0, we have 1. 0 plus 1, we have 1. 0 plus 0, we have 0. 1 plus 0, we have 1. And when we observe C4 and C3, in this case, 0 plus 0, we have C3 equal to 0. 1 plus 0, we have 1. We have 0, 0. So in this case, C4 and C3 equal to 0. And the result here is okay. Yeah, this is minus 5. Definitely, when you press your calculator, right? If you have your calculator, this is my calculator. And when you have minus 5 in binary, it is 4-bit, yeah, the last 4-bit. It is 1011. 1011. Yeah, this is correct. No overflow in this case. Let's look at this case. Positive 7 minus 2. We have positive 5 result. And we add here in binary. We add, we have this, add, we have this, add, we have this, until we have this. In this case, C4 equal to 1, yeah, because we add this, with this, the carry, we have 1 and 1 here, right? C3 equal to 1, and 1 plus 1, we have 0, and C4 we have equal to 1. So in this case, we don't have any overflow also, okay? And this is because the result is within the range. So no overflow in this case. Look at the last case. Both numbers are negative now, minus 7, minus 2, and the result, of course, should be minus 9. Right? This is minus 7, 2's complement, minus 2, we add, we have this, and we observe that C3 equal to 0, C4 equal to 1, and this is minus 9, and of course, minus 9 is out of the range already, and this should be overflow. And look at this sign. 1 plus 1, negative plus negative, negative plus negative, you should have negative result. But in this case, you have positive result. So something wrong already. This case, yeah, this is negative, this is positive, but you have negative result. So negative plus positive can be positive or negative, yeah. So here you cannot check using sign, all right, but you can check whether it is in the range or not. Okay, and here very easy to check. All right, so this is very important information. Yeah, C3, C4, we can from the observation, we can have something like this. If we have C4, C4, C3, and we have the output is V, right? We create the truth table for this. And let's see if 0, 0, 0, 0, the output V should be 0, right? No overflow in this case. 0, 0, no overflow, so V equal to 0. V is overflow, yeah? We call it V. If 0, 1, here we have overflow, so this equal to 1. If 1, 0, we have overflow here, right? So V equal to 1. And the last case is this 1, 1. Here we don't have overflow, so V equal to 0. V equal to 0. All right. So if we have this is truth table, and we have the relation between V and C4 and C3. So this is easy. We can determine, or we can derive the logic equation, right? So this should be C4 bar C3 or C4 C3 bar, right? You can say that V should be equal to C4 bar C3 or C4 C3 bar, and this is clearly an XOR gate. C4 XOR C3 means that we can detect the overflow by using these two signals, C4 and C3, by using an XOR gate. All right. If we have C4, we have C3, and we can have V for any cases. Okay, that is why we can say that overflow can be detected using the XOR gate. Yeah. So for n-bit numbers, we can have the overflow equal to Cn minus 1 XOR Cn. So what does this mean? Means that if our system is 8-bit, yeah, so to detect V or overflow is equal to Cn, if 8, n is equal to 8, so C 7 XOR C8. Very easy. So with this, we can have, or we can detect any overflow for any size, 8-bit, 16-bit, 32-bit, 64-bit, or any bit. Should be no problem now. Okay. Now, from that information, yeah, we can create what is called a comparator. So what is a comparator? Comparator is a circuit that can use to compare two numbers. All right. So for example, we have two numbers, 4-bit, for example, A and B, right? And the output here can tell you whether A is less than B or not, or A is more than B or not, or A is equal to B or not, right? That is the job of a comparator. So how to compare a number? All right, the idea is to use subtract, to subtract a number. So for example, if we want to know whether A is equal to B or not, so we take A minus B. So if the result is equal to 0, what is the conclusion? The conclusion is A must be equal to B, right? If A minus B and the result is positive or more than 0, so A must be greater than B. If A minus B, the result is less than 0, A must be less than B. All right, so we can use subtractor to do the comparison. So now we can have something like this. So this is a comparator where we use the adder to do subtraction, of course. Yeah? We have learned last week that to do subtract, we use adder. But here is the 2's complement number for the sub. All right. So in this case, is x minus y, right? Because remember last week when we want to sub, yeah. For example, we want to sub. We want to do 4 minus 2. What we do is actually 4 plus minus 2. So this is complement of 2 or negative representation in digital hardware. So how to get second complement? To get second complement is we complement and plus 1, right? So in this case, it's the same. This is actually x minus y. So what we will do is we have minus y is actually plus minus y. And what we do is plus. So minus y is the second complement of y. So how to get second complement of y? What we do is y first complement, which is y bar, and we add with 1. Then we can get second complement of y. So this is how. Here, this is y. Yeah, this is y bar, y bar, y bar, y bar, because this is inverter or NOT gate. All right, and we plus 1 here. This is C in. C in, of course, we plus with C in, right? And our C in is 1. So when we complement y and plus 1, of course, this one will be the second complement of y. And the result here is, yeah, we can say that the result here S, yeah, S will be equal to x minus y, because here we have second complement of y here. Okay, so S will be the subtraction, the output from the x minus y. And here to check for the overflow is easy. We know already from the previous example. We can have the C4 and C3 go to the XOR gate and we get overflow. And to know whether the output is positive or negative, it's easy. You look at the MSB, the sign bit, and the sign bit will be from the most significant bit. All right, here. And if this one is 1, means that the result from the subtract operation x minus y is negative. And if negative, means that x is less than y. So to know whether x is less than y or not, we look at this. All right, you have this, and you can know already if 1 means that the result is negative, and if negative means that x is less than y. If n equal to 0 means that the result is positive. If positive means that x is greater than y. Very easy. And the last one is to check whether x is equal to y or not. Means that the result here, s, must be equal to 0. Okay, so if we look at this, if all here are 0, 0, 0, 0, 0, this is NOR gate. And if all 0, z should be equal to 1. Means that if this equal to 1, means that x should be equal to y. But if z equal to 0, means that one of the signal here must be 1, one or more. All right, means that not all the signal here are 0. Z should be equal to 0. So to check whether x equal to y or not, we look at this, and this is the circuit. And from that, we can get the comparator. And this comparator is very important. It is used in computer to compare a number. So for example, in computer programming, right, when you write your program, when you say if A greater than B in your program, all right, this is actually using this comparator circuit to give you whether A is greater than B or not, right? And you are required to derive the Verilog code for the comparator. So this is your homework. So go back, try to write the Verilog code for this. This is not that difficult because you know already how to design the full adder, 1-bit full adder, and also you know already how to use this full adder using hierarchical design methodology to connect this adder to this adder, and this adder, and have logic gate like this, and have extra NOT gate like this. Yeah, in Verilog, very easy. So you can refer to the example, this example on my YouTube video. So it is actually very similar to this. Yeah. Okay, so that will be the comparator, and the next one is the multiplier. So the multiplier is the circuit that is used to multiply numbers, right? So again, when we want to design a circuit that can perform mathematical operation, so we need to understand how the operation is performed in binary representation. Okay, just like what we did in designing the adder, right? So we need to know how to perform the operation in binary. So in this is example of multiplying numbers in binary. Yeah, we learned this already in digital electronic. So for example, 14. This is 14. This is unsigned number. Yeah, 14, and this is 11, unsigned number. We multiply. So 0 multiplied by 1, we have 0. 1 multiplied by 1, we have 1, and 1, we have 1. So every bit, if you multiply by 1, you will get that bit the same result. Yeah, and if you multiply by 0, so you will get 0, and you add here, you add, right, and you get the product, and the product is big. Yeah, here 14154. So you can see that if you have a 4-bit operation, 4-bit multiplied by 4-bit, so the result is 8-bit in this case. So multiplication, normally the result is double from the size of the uh, multiplicand and multiplier, right? And this is how we multiply by hand. But in hardware, this is difficult because here we can do actually we can use AND gate, yeah, to do this. All right, can give you the same result with multiplication, because 0 and with 1 we have 0, 1 and with 1 we have 1, so should be no problem. But here is the problem, right? Because we need to add all these, so we need one adder, and adder. So, and we cannot have adder that can add multiple input at one time. Remember, our adder only has 2 input. All right, we can only add 2 numbers at a time. So in hardware, we need to modify a little bit. All right. So from this, we try to modify so that we can get something like this, where we multiply the first one with this one, we get this one, and we call it partial product 0. And we multiply with the second bit here for multiplier, and we get this, and we add first. All right, we add first here, and we get the result before we get the partial product number 1. We add first. So in this case, we use one adder, yeah, 2 input adder here, and we get result. Should be okay. And next, we multiply again with 0, we get 0, and we add to get what we call the partial product 2. We add here. And the last bit here, multiply by this, and we get this, and we add. And we get the result, the same result as well. So this operation can be implemented in hardware. Yeah, this one is cannot be implemented in hardware, right? So with this understanding, we can have the multiplier circuit. Yeah, using what? Using a AND gate and adder. See, we have add operation, and add operation. So of course we need to use adder in multiplication. So this is how. All right, when we represent the multiplicand with m, and multiplier with q, and for example, this bit, yeah, is called m0. This one is m1, m2, m3. This one is q0, q1, q2, q3, like this. So we can see that when we multiply m0 q0, which is this one, exactly this one, and we can use actually the AND gate here, m0 q0, and the result should be this, and we call this result as p0. And for this one is actually m1 q0, this one is m2 q0, m3 q0, and we have this, which is m0 q1, m1 q1, m2 q1, m3 q1, and we have this. And here, look, we use adder. We add this one, we get this one. We add this one, we get this one. We add this one, we get this one. And we add this one. Actually, we have this also, right? And this is 0 in this case. We add, we get this one. Yeah, because we don't have here, right? So this we connect to 0, we add, and we get this one. And the carry from this is this one. right? And again, we repeat, and we will have all the result here, P0 until P7. Okay, so multiplication for multiplier, when you have a 4-bit, M0 to M3, the output must be 0 to 7, 8-bit, yeah, because of this. And from this, we can have our hardware. So this is the hardware for multiplier. So we can see that M0 Q0, M0 Q0 is AND operation. So we have M0 Q0 AND. So this is AND operation. We have P0. And this one is M1 Q0, M1 Q0 AND operation. And it is the input of the adder. This is input of the adder. We add with M0 Q1. So this is M0 Q1. And we add, and we get this P1. So this is P1. And here again, M1 Q1, M1 Q1 add with M2 Q0, M2 Q0, we add, and we have the output, which is this one. Yeah, we add, and we need to add with another one, M0 Q2, which is this one, M0 Q2. We add and we get P2, and so on, right? So you see, the multiplier can be created using adder, and it is, of course, more complicated as compared to adder. All right, although it is a 4-bit, this is 4-bit adder, and you see, if we have 4-bit adder, how many adder we need to have? We need to have 12 adder, right? 12 adders. In addition, for addition, for add operation, so if 4-bit, we only need 4 adders. But for multiplication, 4-bit multiplication, we need 12 adders, and also we need the logic gate, the AND gate as well. So this is clearly that we can conclude that multiplier is much costly, expensive as compared to adder. So multiplier is expensive. It needs more circuit component, need more space in order to get the adder multiplier. All right, but we have learned already how to design a complex circuit using what we call the hierarchical design methodology. All right, so in this case, we can see something here where the structure is repeated, right? So looks carefully here. Yeah, this one is similar to this one, and also similar to this one. So we can design this one first and make it a module like this. All right, and we connect like this. Yeah, instead of design one by one like this, this is looks complicated, but we actually can have this part as a module, and we connect like this, and we can get the complete multiplier, and 8-bit, 4-bit multiplier like this. All right. So this is how we design multiplier in digital hardware. Okay, and again, you need to derive the Verilog code for this multiplier. Remember, we have learned a lot how to describe the digital hardware, the digital circuit using Verilog code. Yeah. And the last part for chapter 3 is the ALU, or arithmetic logic unit. And just like what I said before, this ALU is very important in digital hardware, and it is almost everywhere in your electronic devices, your mobile phone, your computer, your smartwatch, your everything. Actually, you carry many ALU with you almost every time. In the LU, there are actually the arithmetic circuit. So the LU is the circuit that can perform arithmetic operation that we have learned before. Actually, for example, the add is the component of the ALU. The subtract is the component of ALU. The compare is the component of the ALU, and multiplication also the component of the ALU. And of course, because the name is arithmetic logic unit, so it can perform arithmetic operation and also the logic operation, the AND, the OR, the XOR, depend on the size of your or the type of the LU, right? So this is just an example of the LU, and the symbol is like this, and this is an 8-bit ALU, where we have input 8-bit input for the first A, and the second input is 8-bit B, and we have output 8-bit output here, and we have the flag, what we call the status signal here, and the one that we just learned just now, negative and Z, overflow and carry, right? And this is the operation OP, and the size is 3-bit in this case, because we have how many operation here? We have 8 operation, all right, and each operation is represented by this binary number. So we have 8 unique operations starting from 000 until 111. So if the operation is here, the signal here is 000, so the ALU will perform the add operation. Means that the result here is A plus B. But when we change the signal here to 001, so the result here will be A minus B. Means that our subtract operation. And if we change the operation to 010, this is A compare B. 011, A multiply B. And 100 and 101 or 110 is not B. Means that there is no A in this case. Not B means that the output is complement B. And if the OP here is 111, pass A means that if A equal to 1, so the result here as is equal to 1 means that we just pass the data here from A to the output adds here, right? So we can design this circuit also, and of course the circuit is quite big. We have adder, and of course the adder and the adder, subtractor and comparator is actually the same circuit, right? Multiplier, of course, a different circuit we just have learned just now, and it's just an AND gate, or is an OR gate, not gate, and pass A is just a wire from A to S. So we can design the ALU like this, where we can have A and B, and for 00, we can have the multiplexer here. So if OP is 000, means that the output to S here is from this, all right? And when OP is 001, and again if 001 means that here, because this is at sub circuit, and when this is 1 means that it will perform subtract operation, and the output is from this, this is output operation. And this is for compare, this is multiplication, all right? If the output OP is this 011, so we will have the multiply operation. And if we have this is not 111, this is 100. Okay, so if this is 100, so we have the AND operation, If this is 101, we have OR, and 110 we have NOT, and the last one 111 is just A is passed to the output, and you are required to derive the Verilog code for this. Okay, can you do that? All right, so that will end with the last part of this chapter.